Okay, so I hope I am audible, and I'm Subrata Samanta. I'm a PhD student at IIT Kanpur. So I am a teaching assistant for the thermal physics course taken by Professor Demmala Banerjee this semester at NPTEL. So okay, so let me first share the screen and then discuss. Share screen. Okay, so I hope my screen is visible now, right? Okay, so in the previous class we will discuss briefly about in the previous class we will discuss briefly about thermal equilibriums. That means heat spontaneously transform from one hotter body to a colder body, and when they are in thermal contact, right? Uh, and not in the reverse direction. So it always heat transfer from a hotter body to colder body, and eventually leads to the thermal equilibrium. That means both systems at the same temperatures, right? So that is the way to get a thermal equilibriums. Okay, and so today we will discuss about what is the definitions of the heat. Okay, so first let's say the question is that what is the definition of heat. Okay, so what is the definitions of heat? Okay. So heat is energy in transit. Okay, so heat is energy in transit. So in transit is very important. Okay, so energy in transit. So what it means that things that okay. So let's do some example. What it means that in transit. Okay. So suppose you want to warm your hands by using by the two process. The one process is that put your hands in front of something hot objects, and another is that rubbing your hands. Okay, by rubbing your hands. So the first case you add heat to the systems. Okay, and then we get a final temperature, higher temperatures. But second, we are doing some work done for that for to get the same situation. That means the increase the temperature of the systems. So temperature of your hands. Okay, so that means that you get a same final situations by two different way. So not that the putting heat to a thing, but you get some work done for that, you can get the same thing for in the final state. Okay, so that means heat you cannot you can add heat to an object, but you cannot say that that a object contains certain quantity of heats, right? So there is no meanings that that a object contains certain quantity of heats. Okay, so you can do the same amount of heat doing some work done. Okay, so that is called the energy, the process of the how transfer of heat actually stores the energy in certain systems. So it written explicitly that so you can add heat to an object, but you cannot say that the object contains certain quantity of heat. The object contain certain quantity of heat, right? But they contain certain quantity of energy. Okay, so object contains certain quantity of energy, but not a certain quantity of heat. So heat is always the energy in transit. So that is the basic definitions of heat. So you can add heat to the system, and via different way, putting some energy to the system via different way, via the adding heat or doing some work. Okay. So when we discuss the first law of thermodynamics, so this picture is becomes clear better. Okay. So this is the concept that what is heat, the first concept, and second is called the heat capacity. So but an object, so you can just write that but an object can contain certain amount of energy, can contain certain amount of energy. Okay. So the second concept is the heat capacity. So first we can go into the what is the heat and then the heat capacity. So then you might be asked a question that if there is a so we are previously just few seconds ago we are discussing that the heat is not possible for an object to contain a certain quantity of heat, right? So the not possible for an object to contain a certain quantity of heat, that what is means that the heat capacity of an object, right? So heat capacity is the just that slightly different way we talk about that how much heat, so this that the how much heat needs to be supplied to an object, needs to be supplied to an object to rise its temperature, supplied to an object to rise its temperature by a small amount dt, small amount dt, right? So how much heat needs to be supplied to an object to rise its temperature by a small amount dt, so that is the heat capacity. Okay. So it does not mean that a system contains certain amount of heat. So this is not possible that a system contains certain amount of heat. So heat is always the energy in transit. So heat to be add or supplied to the systems, okay, to rise its temperatures by a small amount dt. So this actually mathematically we written this that the dq is c times dt, right? So you can increase this amount dt by putting here d, and this proportionality constant is your specific heat. So this is the heat capacity. It's not a specific heat. Specific heat we'll define later, but this is the heat capacity. Right. So that means the heat capacity is C equals to dq by dt. So this dq amount of heat supplied to systems to rise the temperature dt. So this is the proportional, and proportionality constant is that the C. Okay. So the C is the dq by dt. So the specific heat capacity, okay, we will denote this a small c and this is a capital C. So this is a capital C is the heat capacity, and the specific heat capacity is just the small c. So this is just the heat capacity per unit mass. Heat capacity per unit mass. Similarly, you heard about the term that the molar heat capacity. So molar heat capacity, similarly the molar heat capacity is the heat capacity per 1 mole of an object. Heat capacity of 1 mole of substance. Heat capacity of 1 mole of substance. So these the two things, that the heat and heat capacity are the important concept. So we will need this concept further when we go to discuss on the law of thermodynamics. Okay. So okay, so then I will go into the things that, yeah. So now that we are denoting this the heat capacity for any object, any kind of substance. Okay. So then what about the gas? So you had that the heat capacity for a gas, there are two things. One is that heat capacity at constant pressure and constant volume. Okay, so why these two different things are comes into the pictures? So when we discuss that the heat capacity for a gas, so heat capacity for a gas, okay, just a minute. Yeah. So okay, so we just discussed that the concept of heats. Okay, and heat is the energy in transit, and so you can add heat to an object, and but you cannot store the heat to an object. Okay, so heat always the motion, the energy in transit, always the in transit motion. Okay, you cannot add and subtract some amount of heats. So you add heat but cannot store or cannot remove something. Okay, you cannot store the heat to an object. And then the concept of heat capacity. So heat capacity is that the how much heat needs to be supplied to an object to rise its temperature by a small amount daily, and this proportionality constant, it gives the heat capacity. So when we discuss the heat capacity for a gas, yeah, so when we discuss this heat capacity for a gas, so that means there are two things. So let's say we consider a box, okay, and they contain some gas molecules. So by definitions that we increase its temperatures dt. So we increase its temperature, let's say we adding some dt heat. Okay. So we add heat to the systems. That means gas molecules becomes randomized and increasing the kinetic energy, this kind of things. So it may be this container volume increases or pressure increases, right? So there are two things happen. So if you say that your volume is fixed, that means your box cannot modify it, the size of the box cannot modify it, but you when you are adding heat, right? So that means your pressure increases, right? So that's why there are two situations appears for in this case. So one is that the constant volume. So that means when you add heat, okay, so increase pressure. So that is called then the heat capacity is called the CV. The heat capacity at constant volume. So that means the volume is fixed and the pressure will increase. So when we adding heat, the corresponding pressure increases. Okay. So this is the CV. The other possibility is for these systems. Okay, so if we say that the pressure is constant, that means let's say the system this, and there is a piston, okay, and the gas molecules are there. So now we again adding some heat to the system. So when we add the heat to the system, we say that the pressure is constant. That means this piston lifted upward slightly, the volume increases. The volume of this area of the gas molecules. Uh, so, so volume is that the where the gas molecules content. So this slightly increases. So in this case, the pressure constant just okay. So pressure constant, that means the volume. So when we adding heat, so adding heat, that means that the volume increased. Volume increased. So this is called the Cp, is dq by dt, and this is get the Cp dq by dt at constant volume. So for gaseous case, there are two situations, Cp, and for other objects, so we just call the heat capacity. Okay, so this is the concept of heat capacity. Okay. So now we are going to discuss just a minute. Yeah. So now we are going to discuss the okay. So till now we are the heat capacity becomes the concept of this are clear now, right? Any questions further? Okay. So now we are going to discuss the key concept of thermal physics, that is called the energy. So it's the energy. Okay. So that means what happens when energy is changed from one form to another. So energy is a different form, right? So you can add a you can doing some same amount of energy by via some work done or putting some heats, different way. So how the energy transform from one form to another. Okay. So then so you know that the what is the system? The system is called that so the thermodynamics. So we can define a system, that means the region we are interested. Okay, so it's called the system, and so this is the region that we are interested. Okay, it's called the system. Okay, and outside of this system is called the surrounding, and whole is the universe. Okay, so universe is contains both system and surrounding. Okay, so then we discuss the functions of state. So when a system, so energy is a functions of state. That means that what is the functions of state? Okay, so let's write the question first. So, what happens when energy is changed from one form to another? So this form means that which form they are contented. They are in heat way or adding heat way or doing some work done. This kind of form. Okay. So one form to another. Right? What happens the energy when it changes from one form to another? So then we discuss the first thing we have discussed, that the functions of state. Functions of state. So a system, when a system in thermal equilibrium, so when a system in thermal equilibrium. Okay, so when a system in thermal equilibrium, right, so then all the macroscopic observables properties are fixed. All the macroscopic observables properties fixed. So macroscopic means that the whole systems, okay, the pressure, volume, okay, and temperature. So temperature of the whole systems. Okay. So we are not tracking to the individual molecules. Okay. So we are treated as a whole system, and when this whole system is thermal equilibrium, that means we have a definite amount of pressure, volume, and temperature. So okay, these are fixed. So and we are not interested in how they got this value. Okay, so we are only interested that what is the final values of that. So this the macroscopic observables properties are fixed. That means that what is the macroscopic observables? It's just a pressure, temperature, volume, okay, energy. So these properties are the functions of state. Okay, so the definition is that the functions of state is any physical quantity, is any physical quantity that has a well-defined value, that has a well-defined value for each equilibrium state of the system. For each equilibrium state of the system, right? So for gaseous systems, the functions of state is the pressure, temperature, volume, energy. So when the system is equilibrium, so these quantities are fixed. When we change the system from one equilibrium state to another equilibrium state, then this value got changes. But one equilibrium state, these values are fixed. So this is the functions of state. Okay, the definition. So this is actually the independent of, yeah, so independent of how they got there. Independent of how they got there, right? So this is the how they got there. This is the independent. Okay. Yeah. So any question? Okay. So okay. So that means that if you know that in thermal equilibrium, that means there is a no time dependence. Okay. So that means the functions of state is also there is a no time dependence. Okay. So it's all our quantities, physical quantities are time independent, because you are only considering the thermodynamics and in the thermal equilibrium system, so there is no time dependency comes into that, right? So which quantities are not a functions of state? So these things are the functions of state, right? Pressure, temperature, volume. But which quantity are not a functions of state? So example is that. So suppose the total heat put into the system. So total heat put into the system. Right. So this is not a function of state. Second, total work done on a system. Total work done. Yeah, so total work done on a system. So these are not functions of state. So these are not functions of state because they depend on the how we are putting heat into the system. Okay, depend on the path. So mathematically, so how to express mathematically? So mathematically, this let's say f of x is a some functions of state. F of x, some function of state. So that means when we change from x1 to x2, okay, so there is a so when we and x is a, so this x actually is a set of x1 x2 x, a set of points. Right. So let's say we consider there is a x1 point here and there is a x2 point there, and we can treat this x1 point as a origin. So in this case x, and this is f of x. Okay. So there are 2 points x1 and x2. Okay, so that means when we change from xi to, okay, so this is not x2 point this and the f of x to this. Okay, so the delta f, the change of f when we go x1 to x2, that means x1 to x2, when we go the x1 and x2, delta f is this df, right? So this only depend on the x2 minus x1. Okay. So this only depend on the x2 minus x1. So this is not a path dependent, that how to go this x1 to x2. So in this way, this is the one path, this is the two path. Okay. So one path is go to that this point to this point directly, and you go from this way and then go to this way. This is the second path. Okay, so let's changing the color. Okay. So you go this path 1 or go to the path 2, that is this way. So it's exactly the same thing. Okay, so it depends only on the end points. So where the value here and where the value here, that just depend on that is the functions of states. Okay. So that means this df is exact differential. So when we integrate, this only depends on the endpoint, that is called the exact differential. So if f is a function of state, f of x is some functions of states, then df it must be exact differential. If this is not a function of states, so if f is not a function of state, this implies that df is inexact difference. Inexact difference. Okay. So you cannot write that as just subtracting these endpoints when this differential is inexact. Okay, so let's do one example that suppose consider a if the function is x and y. Okay. So this is your if. So this is a mathematics just, and then we can write down the df. So this is d of xy, that means x dy and y dx. So now we are changing this from let's say 0 0 0 0 to let's say 1 1. So we are going this point to this point. Okay, we're calculating this df. So that means the delta f, we are going this 0 0 point to 1 1 point. The change in delta f, this point to this point. I'm not till now I'm not denote the what is the path is. We're just setting that the point, and then df. So then we calculate this if you know this f of xy, so you just put is the value. So xy 0 0 1 1 get a 1, right? So this answer is independent of the what is the path. You consider any path, but you write in this way. This is the exact difference. So suppose you consider now we are going to that the another things. Let's say your y dx. Okay, so x dy and y dx, right? So your f is xy. Now we are considering only one. Let's say x dy or y dx. Let's say y dx. So if you only consider the y dx function, let's say dg, d bar g. Let's consider. So the claim is this is the independent of path. Independent of path. That means that df is exact. Exact difference. Okay. So this df is exact difference. So now if we let's consider d bar dg is y dx. Okay. Now we are calculating same thing. The delta g is 0 0 to 1 1 dg, right? So that means if you get that dg is y dx, so 0 0 to 1 1 y dx, what do you get? Your x is variable, so only x limit are taken into account. So y dx, so that is this is half, right? So y square by 2 and half. So now if you, but when this integrate yeah, so now the same thing, suppose this integrate not carried out along the line y equals to x, but along the path, let's say so this integral, that means we are taking y equals to x line. So this integrate we are taking this one, so we are getting 0 0 to 1 1, yeah, so we are going to 0 0 to 1 1 y dx, and by taking this line that x equals to y, this line, okay? Yeah, yes, so you are going to this line, okay? This line is that y equals to x. Okay? So we put y equals to x and limit that dx, right? So we get a half. Now we are consider this the same integral do in this way, that the same 0 0 to 1 1, but we are going to different way. First go to this point, this point is 1 0, and then go to this point 1 0 to 1. So the same thing, if we change the value, so that 0 0 to 1 0, that means 0 to 1 only vary dx plus 0 to 1, so in this case the x vary, right? So only x limit 0 to 1, so x limit 0 to 1, 0 to 1, x vary. In this case y vary, so this path y vary, right? So then the y limit 0 to 1, y limit 0 to 1, because another is fixed, so x is fixed, x1 x1, x is fixed, but y vary 0 to 1, so y vary 0 to 1, y dx. Just a minute. X fixed, y vary, so how to write, yeah, okay, so there is a two variables, 0 0 to 1 0, and in this case 1 0 to 1 1, again y dx. So you see that in this case you put that the y is fixed, that means y value in this path y value 0, this path y value 0, this path x equals to 1, right? So this is 0 because y value 0, and this part there is a no variation of x, so 1 0 to 1 1, this path there is a no variation of x, no variation of x. This implies that dx 0, so again 0, so this is a 0. Okay, so this point is clear or not? So that means we get this path, in the first case, case 1, we get this half, but in case 2 we get 0. So this y dx, this is not a function of state, so it depends on the path, okay? So which path we are calculating, and the change of this quantity, this delta g, is actually vary when the vary with path. Okay? When the path varies, the different path different get the answer. Okay? This is not a function of state. Okay? Just one piece of df. Df is a function of state. So this df is a function of state, but this y dx is not a function of state. Okay? Similarly, x dy is also not a function of state. Okay, x dy is not a function of state. Okay, but the combination x dy plus y dx is a function of states. So that means that y dx, so if this is not a function of state, then the differential will just be cut, okay, just for the differentiate with the functions of state and not a function of states. So this is d by g, this is just cut over a derivatives. So d by g is y dx is not a functions of state. Similarly, we calculate d bar, let's say w is x dy is not a functions of state, but df is d bar g plus d bar w. Okay, that means that x y dx x dy, okay, is a function of state. Is a function of state. Okay, so this point is clear or not? Yes. So now okay. Okay, so now I just quick review that the functions of state and the equations of states are connected actually. So suppose we say that the if PVT equals to 0, right? So pressure, volume, temperature, and the sum functions of pressure, volume, temperature, this is a 0, right? So that means that so this the gas for a certain kind of gas, so this f of PVT actually 0. So this is a functions of states. Functions of state. Similarly, we say that the from this case that PV actually, let's say in KVT, right? This is the equations of state. Or go to the complicated things. So this is for the ideal case, but for any case, a PVT is 0, right? So the functions of pressure, volume, temperature, we are going to on side that PV minus NKV equals to 0. So function is this kind of functions. So define different function, define different equations of states. Right. Okay, so now from this, so this is the workout example that we are done previously. So this is actually closely connected to the first law of thermodynamics. Okay, so in the first law of thermodynamics, first law of thermodynamics, so what is the statement of the first law of thermodynamics? That means the energy is conserved. Energy is conserved, and heat and work are both form of energy. Heat and work are both form of energy. Okay, so this is the statements that energy is conserved of a closed systems. Okay, so we are considering that the systems, and heat and work are both form of energy. Because we are dealing with the thermodynamics, okay, and there is a no time dependence, the system in thermal equilibrium. Okay, so then we can write the internal energy So the change in internal energy, that means that the mathematically that the change in internal energy, change in internal energy, delta U is delta Q plus delta W. So we adding some heat, delta Q and delta W. So delta Q is the heat supplied to the system. So delta Q is the heat supplied to the system, and delta W is the work done on the system. This is the to the system and work done on the system. So when we change some energy, so energy is actually stored in the system, right? So when we change some energy in the system, so we put some heat to the system, okay? So heat supplied, heat put to the systems or work done on the system. Okay. So similarly, suppose you warm your hands, right? So rubbing your hands, you do some work on the system. System is your hands, or if you put your hands something hot objects, the heat transfer from the hot object to your hands, and your hands actually leads to that final temperature T, right? But you can same thing, but not putting heat, not putting your hand near to the warm object, but because something hot objects, you can do some work, okay, rubbing your hands, and you can get the same thing, okay, you can get the same final state temperatures, okay. So that is that, okay. So you can work done on the system, or you can heat supply to the system, you can get the same energy, okay, or temperature, same thing, okay, in thermal equilibriums. So yeah, so the convention is that so del Q is positive, that means we are supply to the system, okay. So this del Q is positive when we heat supplied to the system, okay, and other things are negative. So when we heat extracted from the system, that means the delta Q is negative. So that is the convention. So we read only one. So heat supplied to the system, it is positives. When we heat extract from the system, it's negatives. And similarly, the work done is positive, that means the work done on the system. And so what it means that in this case that the negative. So negative means that the system work on its surrounding. System work on its surrounding, not that the system work done on the system. So system work on surrounding and is positive. So negative means that the system work on its surrounding. So they are things very confusing. So okay, why what the convention? Okay, what is the positive, negative? You go into the different books or different literature, you may that the reverse things happen. Okay. So the convention must be clear that the negative means that the system work on its surrounding, and positive means that the work done on the system, work done on the system. So on the system, on its surrounding. Okay. So then we can go to the things where we discuss this, the system and surrounding. So system and surrounding are two different things. So these systems that we are interested in the regions, okay, that is the system, and the outside is the surrounding. So system work on surrounding. Yeah, system work on surrounding, or you can work done on the system. Two different things. So one is positive, another is negative. Similar way you keep putting, you can adding heat or extracted heat. So this convention is clear now, right? Okay, so then for a small change, okay, for a differential change. So for a differential change, okay, differential change means that the infinitesimal change. Okay, so for a infinitesimal change, this du is dq plus d. So again you get that dq is a function, du is a function of state, but dq is not a function of state, and dw is not a function of state, but dq is a function of state. So this is the first law of thermodynamics. So we'll do that the workout example that here, that df is not a function of state, but dg is a function of state, df is a function of state, and dg is not a function of state, and dw is not a function of state. That's why we put cut on the derivatives. So the first of thermodynamics is the same thing. So du is a function of state. So this is a function of state, and this is not functions of state. So these are the inexact differentials. Okay, so we put cut on this. So how to know that this thing? So this is very simple, that so let's say dw. So dw means that the work done, and this is that the heat. So somewhere writing, yeah. So this is the work done, and this is the heat. So let's say you so stretching a wire. Okay, so the work is that we putting a force F, and is displaced the wire is x. What is the work done? dw is a f dx, right? So applying a force F, okay, and for dx displacement, the work done is f dx. That is the definitions. Right. So as you previously see that this kind of thing, that y dx or x dy, right? So x y anything, but in this case that the y is f and x is x. Okay, is the distance, and y is force. So f dx. So this is the inexact. Similarly, when the work done by compressing a gas. So this is a kind of chain problem, but similarly we can do, let's say, a gas, and there is some piston. Okay, so we can increase the volume, this v to, let's say, dv. So this we can increase this v to dv. So the work done dw at constant pressure minus p dv. Why there is a minus sign? I'm coming to this point. So this dw we can at constant pressure p. Okay, so we increase this volume v to dv, v plus delta v. So I think we can reach this level. So just doing a different colors. Yeah. So this is a dv. So this is a v, and this v to dv, v to v plus dv. So this is the work done at constant pressure, dw actually, minus p dv. Okay, so minus sign ensure that the work done on the system is positive when dv is negative. So as I say that so you put the work done. So in this case, the system work on its surrounding, right? So this is the system work on its surrounding. So if you work done on the system, so that means the work done, the work dw, okay, this work dw, work done on the system when dv is negative. This point is clear. So when dV is negative, that means you are reaching final level here. That means you work done on the system, right? So when dV is negative, that means the dW is positive. So my convention is that when you work done on the system, that means the dW is positive. So dW positive means that the dV is negative. Okay, dV must be negative, and if dV is negative, that means that you work done on the system, because your initial volume V and you work done on the system, your volume is V2 V minus D. If the system work, right? If the system work, that means that system volume V, and if the system work, then the system volume is V2 V plus dV. So dV is positive, then the system work. So it's a negative sign. That's a sign convention is so this minus sign is clear or not? Okay. And this equal sign, again, the another thing is that the equal sign. So the equal sign is also important. So this equal sign ensures that's for a reversible process. So this ensures that the process we are doing this volume changing, this is the process that how to change the volume V to V plus dV or V minus dV is a reversible. That means slowly. You cannot just put the piston and slightly at a certain time we fall into this. Okay. So this process is not that equality sign. Okay. So this equality sign ensures that your process how to change the volume is a reversible. That means every point you are going back and forth with the same thing. Okay, the reversible process. So ensure that your process ensures that that the process is a reversible. That the process is a reversible. So if the process is not reversible, then dW is not just equal to minus PdV. Is the less than or greater than equals to PdV. So we will later discuss that for a irreversible process, is dW less than or greater, which things are happen. So when we discuss the irreversible process later, we will talk about those things. Okay. So, but in this case, we just memorize that the equal sign means that the reversible is the reversible. The process is reversible. That's why we write the equal sign. Okay. So that the reversible, that means that your piston is the frictionless. So your piston is frictionless. So you can so reversible. How to get a reversible process? So reversible process by slowly changing the pistons. Okay, and if the piston is friction, let's say there is some possibility we can go back and forth, right? So there is no extra. It's a process, man. So you can go in the forward direction or you can go the backward direction. So it's the same way. Okay. So that's why the process is reversible. But when you suddenly jump to the piston slightly, that this process is not a reversible. Okay, so then we are going into the again the heat capacity for in general systems. So we'll discuss at the in the beginnings that what is the heat capacity, but here we do some mathematics or some problems related to the heat capacity. Okay. So let's first do a simple problems that suppose a two system. Let's consider a two system, one system at temperature T1 and another system at temperature T2. So we put add heat to the system, we had also heat to the system. Okay, so this dq we can heat add to the system, dq, it's a dq1 dq2. So dq1, if we change the temperature T1 to So due to this due to the due to add heat to the system, the changing the temperature T1 to T1 plus dT1, and this changing the temperature T2 plus dT2. Okay, so dQ1, what is the dQ1 then? Means that how to write this dQ1 in terms of dT1, because due to dQ1 the temperature change of the system T1 to dT1, T1 to T1 plus dT1, right? So that means this dQ1 related to this dT1. Okay, so how to write this dQ1? So what is this proportionality constants? Yeah, so go back to here. Okay, yeah, this point. So this is the definition of the heat capacity, right? So dq is c dt. This proportionality constant actually the heat capacity. So just to recall the thing that how much heat needs to be supplied to an object to rise its temperature by a small amount dt. That is the definition of the heat capacity. Okay, see. So then we write this dq1 c1, sorry, c1 times dt1. Just a minute. No. Okay, so dq1 actually c1 dt1, similarly dq2 c2 dt2, right? So the specific heat of the system 1 and this is the system 2. So the specific heat of the system 1 is c1 and the specific heat capacity, and the heat capacity of the system 2 is c2. So now we connect this two systems via a thermal contact. So we are putting the two systems via thermal contact. So that means your system 1 is thermally contact the system 2, right? And this is thermal contact. So what happens when we putting this two system in thermal contact? So recall the thermal equilibrium situations. Okay, so what happens when we the two different temperatures and we put this two system in thermal contact? What happens at final positions, at final steps? Yes. Yeah, so that means the whole system at reached at final temperature, some final temperature Tf, right? So when the temperature not equals the heat flowing from one system to another, right? So the final situations that we are going to one system is the final temperature Tf. One system is that the whole systems. So now the system is treated as a one system, and the whole system temperature is the Tf, right? Yeah. So how to calculate this Tf in terms of this C1, T1? So what are the input parameters? That the C1, right? So the heat capacity of this C1, heat capacity of this C2, temperature T1, temperature T2. So once we know this C1, T1, C2, T2, so these are the inputs, we calculate this final temperatures. How to calculate this final temperatures? PF. So yeah, how to calculate? Any idea? Okay, so we know this relation, right? dq/dt, right? So that means, let's for a moment consider that T1 is T2 is greater than equals to T1, right? So that means the heat must be flow from the T2 to T1 because T1 is greater, right? So heat must be flowed in this direction. So let's write in the red pens. So if this condition T2 is greater than equals to T1, then heat must be flow this direction, right? Okay, so that means, yeah, so that means heat extracted from the system 2. So what is that? dq, what amount of heat extracted from this system? C2 dt2, right? And what amount of heat put in this system? Same amount of heat. Sorry, I'm just okay. So this the amount of heat extracted from this system delta Q is C2 T2 minus let's say final temperature TF. Right. So we are going these situations to this situation. That means that the second system temperature changes T2 to TF, right? So this T2 to TF, the amount of heat. So TF actually in between T1 and T2. This point is clear or not? So T1, TF, T2, because TF is equilibrium. Okay. So the TF temperature must be in between these two temperatures. Okay. If one is higher, if one is lower. Okay. So that means that the heat extracted from the system 2 to this final position TF, that means the TA to TF, this Poriman heat extracted, that means the negative sign. Okay, we will the sign conventions imports later, but similarly the same amount of heat input in this system, right? So that means that the amount of heat adding to the system dq is C1 TF minus T1. Okay, or you can write this T1 minus TF. We do not know, but we put a negative sign here. So that means when we equality this thing, see, that means the C1 T1 minus TF. So this amount of heat extracted, and here the amount of heat added. So your sign convention that when the heat extracted from the system, we put a negative sign. That's why we put a negative sign. And here we have add to the system, we have a positive sign, right? So that means your C1, and we can equal it to this delta Q, the same amount of heat extracted from the system, and this amount of heat actually added to the system. That's why they are thermal equilibrium. So then we can equal to this thing, and C2 is T2 minus TF. So then we can calculate this TF is C1 T1 C2 T2 by C1 plus C2. So you calculate the final temperatures of the systems. Tf is Tc1, T1, and C2, C2 by C1 plus C2. Or if you not put in the sign convention minus plus, we just say that this del q is extracted and this same amount of heat just put it, then this sign is Tf minus T1. So in the same way, you can tell that the at the end you will get the same answer. So what your convention that it does not depends on the answer. So you can choose any conventions, but the answer is can the same. So this point is clear or not? Any questions or you got? Okay. So yeah, so that is the first problems, and then we are yeah. Okay. So now we are going to into details that how the internal energy of a gas changes when we add heat to the systems. So questions that how adding how the internal energy of a gas, how the internal energy of a gas changes when adding heat. Okay. When heat. Okay. So now we are going to discuss rigorously that these questions. Okay. Okay. So what we learn so far that for ideal gas, so what is the energy U for ideal gas? For ideal gas, okay, so there is a no potential energy, only kinetic energy, and just tell from the equiperson's theorem. Is it right? Right? 3 by 2 R for ideal gas. So that means this energy it only depends on temperature. But in principle, this is not true, right? So when we discuss the van der Waals gas, not the ideal gas, the real gas. Okay, so the previous class, just recall your previous class that when we discuss this van der Waals gas and okay, so yeah, so you see this equation. So the energy is not depends on temperature, but also depends on the volume. It also depends on the volume, right? So yeah, so it also depends on the volume. So when we're doing the ideal gas, when we're dealing with the real gas, we see that the energy is not depends on the temperature, but also volume. So in principles, you see that so it taught about that macroscopic observables, that PTVE, right? So these are the 4 macroscopic observables, right? And their defined value or the fixed value at each equilibrium, each thermal equilibrium state. So this is the for gas, for gaseous system. These 4 so for gaseous gaseous system, this 4 functions of states. Okay, so thermal equilibriums and these microscopic observations are fixed. That means we can retain any of this quantity in terms of others. So this energy can be written in terms of PTV. So in principle, this energy can be written in terms of other variable PTV. This is true. How can go this three variable to two variable? So this is a PTV. The energy depends on the other three variable PTV. Now my question is that this PTV all are independent or they somehow dependent? How? Yeah. So that means they are related via equations of state. Okay. So they are related via equation of state. So that equations of state, what is the constants? As I said previously, right? When you just remember that things that yes, I say that yeah, f of pvt 0. So that means there is some constants p, v, and t, right? So we get one. We can return any two in terms of other ones. Okay. So it's if pvt 0. That means we can return that p in terms of Vt, right? Is only Vt are independent, and you can write the pressure in terms of temperature and volume, and this gives you to the equation of states of the system, right? So that means we can just write E, T, and V, right? So this is the thing, and E is not. We are writing this energy is U. Okay, so just change this thing. So this is, yeah, this is U. This is U. Okay. So yeah. So U can be written in general T and V. Then you recall your mathematics mathematical course that we can write this du, the change in u. Okay, how to write this del u by del t with respect to the first derivatives when the second derivative is the second variable is fixed dv and dt. So this is just a partial derivatives. Okay, so del u del v and your first variable fixed and dv. That means you can change the u, because u is a function of two variable t and v. You can change u in using the variation of the t or using the variations of the v. Both are included. So that's why the variations of t dt and the variation of v dv, when we vary the temperature, the coefficient is that the del u del t by v. Okay, and similarly when we vary the volume and the change in du, they are proportional, but the proportionality constant actually del u del v t, and write the superposition. So this equation tells that things that this du, the variations of the du, okay, depends on the variation of the dt and the variations of the dv. So okay, so now just write down the what is the first of thermodynamics du. So first law of thermodynamics tells you that du equals to, what is the first law? Yeah, so dq we write this card because inexact, and dw, and we can write this dw actually minus pdv for gaseous systems. So dq minus pdv. Okay, so that means so now we are so we are equating this 1 and 2. We get that dq is del u del t v dt plus del u del v t plus p dv, because p dv now add. Okay, we are written dq, just replacing this du dq minus p dv in the equations 1, and we get this thing. So that means dq by dt is del u by del t v plus del u del v t plus p times dv. Right? So this dq by dt is the heat capacity, the definition of the heat capacity C. So when we writing that so this is the heat capacity. Now we are going to the specific thing, that the Cv at constant volume at constant temperature. So when we say that the constant volume, that means your dv 0, because volume is constant. So this del u del t v, okay, at constant volume, this implies that dv 0 no 1 minute yeah, right. And what about the Cp? So Cp is this, means that the del q by del t at constant pressure. So that means no quantity here will be 0. That means that del u del t is v plus del u del v t plus p at constant temperature plus p into del v del t at constant pressure. At constant pressure. So this is your Cv, this is your Cp for in general gaseous systems. Okay. So whatever your ideal gas or real gas, so this is the true for in general gases. Okay. Because the internal energy U is not just the functions of T, is also the functions of volume. Okay, so that's why the del E del V is also taken into account in case of Cp, not in case of Cp. Cp is just in the case of ideal gas, but Cp is not that things. Okay, so that means when you calculating this Cp minus Cv, so this is del U del V at constant temperature plus P, just subtracting this, and del V del T. So this result is very important. So the Cp minus Cv is for in general gas this. Okay. So let's say we are calculating for the ideal gas. The ideal gas is a monatomic gas, right? Ideal gas is the monoatomic ideal gas. Very specific. Monatomic ideal gas. One example, the monatomic ideal gas, that is del U del V at T equals to 0. What is the relation? That U is 3 by 2 RT. We just write in few times here. So this del u del v, that means the u is only function of temperature. In this case, the del u del vt is 0. So then, but one more thing is that del v del dp, right? So what are your equation substitute? Pv equals to RT. So that means v is RT by p del v del T at constant pressure is R by P, right? And just derivative this V with respect to T at constant pressure, that means that R by P. Okay, so R by P. Now we put this Cp minus Cv equation, Cp minus Cv equations. We get that P is del U del V 0. So P and del V del Dp. So R by P. So this is R. So for ideal gas, Cp minus Cv, okay, is equals to R. But not, this is not true in general. Okay. Then we can write the more complex expressions of the du. Okay, so du is that del u del t v dt and del u del v dtv, but del u del t v is always cv, right? So that means that du is cv dt plus del u del v dtv. For ideal gas, du actually is cv dt, but for in general, the change in energy is not just the severity, it also depends on the volume. Okay, so now what is the adiabatic index? The adiabatic index is that the defined adiabatic index is gamma is the ratio of the Cp by Cp. So now we know the expressions of the Cp by Cp for arbitrary gas. Okay, for arbitrary gas, this is your Cp, this is your Cv. Now we divide this Cp by Cv, we get a adiabatic index gamma for arbitrary gases. Okay, so now we are going into the assignment problems. Yeah, so any questions so far? Yeah. So how do we learn so far? So the functions of states have exact differentials, and the first of thermodynamics state that the energy is conserved, and heat and work are both form of energy. Okay. For a reversible process, we know that the equality sign hold. If the irreversible process, then the equality sign is not hold. There is a non-equality, and we know that the Cp and Cp, the expressions of the Cp and Cp for a in general gas. Okay, and then we can calculate the adiabatic index for any gas, is ideal, dl. Okay, so we can calculate this adiabatic index. So next day we talk about the process, okay, isobaric, isochoric, and how to calculate the thermodynamical quantities. Okay, so the mathematical parts, okay, discuss. Now today we're going to discuss the assignment problems. Then if get some times, then we discuss about some okay, so I think, okay, so first look into, let me check the assignment problems. Yeah. Okay, so in the assignment, okay, so just briefly tell about that what is that the isobaric and isochoric process. So now we are going to discuss briefly about the thermodynamic process. Thermodynamic process. So thermodynamic process, there are two processes where mainly the discuss that the today is the isothermal and the adiabatic. Okay, so one is the isothermal process. So what is meant by the isothermal process? Isothermal means that that at constant temperatures. Okay, the process at constant temperatures. Right. So at constant temperature process, that means the isothermal means the constant temperature process. So constant temperature process means that dt becomes 0, right? No variations of the temperature, dt 0. So then if you so if you say that dt equals to 0 for ideal gas, let's consider the ideal gas for an example. PV equals to 0. How? Because so du equals to 0, right? Because du for ideal gas Cv dt, so du equals to 0, right? So that means your first law of thermodynamics tells that du is dw plus dq, so that means dq is minus dw, right? So then we can just calculate the work done or the change of heat. So that means the work done and the change of heat are the identicals, right? So you can calculate the change of heats. Change of heat delta q is that the integrate of dq. That means dq is minus dw. So dw is minus pdv. dw is minus pdv. So you can write this pdv, and you are changing volume v1 to v2 because you are so this process is a constant temperature, right? So that means your volume it changes v1 to v2, right? So now we know that the equations of states that p is actually RT by v for ideal gas. So you just replace this RT by v dv, and your volume is v1 to v2, right? So this is your changing dv, right, at constant temperatures. So then we just calculate this, we get that RT ln v2 by v1. Similarly, you calculate for van der Waals gas. We're just putting the equations of state, the corresponding van der Waals state, and then doing some calculations. Okay, we get this. So so that means that this V2 is greater than equals to V1. V2 is greater than equals to V1. That means your delta Q is greater than equals to 0, right? So this is the case, right? So that means you putting heat in to the systems. Your pressure is constant, okay, and your temperature is constant. Your volume must be increased, right? So this is the case. So similarly for the you calculate let's say the adiabatic index. So second process is the adiabatic process. So isothermal process, and second process is the adiabatic. So adiabatic process of an ideal gas means that the without flow of heats. Okay, so we are not putting any heat. They're not transfer any heat to the system or from the systems. So one yeah, yeah, so they are not transferring any heat to the system or from the system. Okay, so then in this case that means that the, the process is the thermally isolated. The process is thermally isolated. This implies that dq equals to 0, right? So then the first law of thermodynamics tells that du equals to dw. So now we calculate this, for ideal gas. Let's say again the example is ideal gas. So we just putting this du, the CVDT, and dw is minus PdV. So the pressure P actually minus RT by V. So CVDT is minus RT by V dV. Now doing the integrated. Okay, so dt by T and dV by V. Once you do the integrate, we get this T V to the power gamma minus 1 equals to constant. Right. So gamma actually is Cp by Cv. And the ideal gas is Cp minus Cv by equal minus. This difference is R. We calculated, right? And this is gamma. So once you do these things and just first doing first integrate and then just changing this. Okay, so you get this result. So now you use the equations of state. PV equals to RT. So we go another two relation is that P to the power 1 minus gamma T to the power gamma equals to constant. Just put V with replaced by RT by P. Okay. Then we can relate this P and T. Similarly, we can go as just replace the T with RT by V and so T with replaced by PV by R, and we go to the PV to the power gamma equals to constant. Okay. So we can use any of these three forms. Is related with T with P and P with T and P with P. Okay. So we can use any of this for the adiabatic process. Okay, so now we are going to the assignment. What are there? Yeah. So another process and the other two processes. So isothermal means that the temperature constant. Adiabatic, this means that the thermally isolated system, the heat is not transferred from that to the system or from the systems. And there are other two processes. It's called the isochoric process, the volume constants. Okay, and isobaric process is called the pressure constants, right? So other three processes, let's say isochoric process. This process is a volume constant, and char is that the isobaric process. The pressure constant. Okay. So your variable is that the pressure, temperature, volume. So if these are constant, then we can get this isobaric, isochoric, this kind of things. Okay. Just a minute. Okay, anyway, so okay, so there's a two process, and then yeah, so other things are that if the energy is a state functions, right? So that depends on the only the end points. So if a process is cyclic, then you know that what is the answers of this. Okay. So now the calculate the work done of a gas during a quasi-static isothermal expansion from a volume. Okay, so let's do one examples. So let's this kind of examples. So let's say an ideal monatomic gas and ideal monatomic gas and a diatomic gas and a diatomic gas is adiabatically expanded from pressure volume is adiabatically expanded from, let's say, P1 P1 to P2 V2. Find out the ratio of the work done for the monatomic gas and diatomic gas. Find out the ratio of work done for the monatomic gas and the diatomic gas. And the diatomic gas. Okay, so yeah, so how to calculate this work done? Okay, the same way we do just yeah, so how to calculate the work done for an ideal monatomic gas and diatomic gas. So first you calculate okay, so in general I written the expressions for the in general. So we calculate the work done means that the dW, you know, this is a minus PdV and your volume V1 to V2. Right? Yeah, sorry. Okay, so in general is that the your pressure P1 V1 to P2 V2. Okay, and so once you calculate this thing, we get expressions that yeah, okay. So dq0 du 1 minute and dq is 0 for adiabatic process and du actually dw. So yeah, so we calculate these things for ideal gas. We get these relations that P1 V1 minus P2 V2 by gamma minus 1. So this is a W. So when we integrating over this, we get a W. Right? So P1 V1 and P2 V2 by gamma minus 1. Okay, so Then we just put into this formula. So for monatomic gas, for the gamma, for monatomic gas gamma, so it's 1 plus 2 by F, right? What is the formula? 1 plus 2 by F. F is the number of degree of freedom. Number of degree of freedom. For monatomic gas, the number of degree of freedom is 3, right? For monatomic gas. So it's 1 plus 2 by 3, it's 5 by 3, right? For diatomic gas gamma is 1 plus 2 by 5, right? We are only considering translation and rotational, okay? At moderate temperature, we are not considering the vibrational. So that's why 1 plus, sorry, this means that the 7 by 5. So you know that the for gamma, so that means the work done for monatomic gas, right? Monatomic gas by work done for the diatomic gas. So it's just things that so P1 V1 and P2 V2 are both cases same. So that means that gamma diatomic minus 1, gamma monatomic minus 1, right? So 7 by 5 minus 1 by 5 by 3 minus 1. I will calculate this thing. Okay. So these are the things, and similarly we calculate for the other gases. So the polytropic process is that yeah. So the similar, okay. So the polytropic process. Polytropic process is that the p v to the power n equals to constant, right? So adiabatic process is p v to the power gamma equals to constant. The polytropic process p v to the power n equals to constant, where n is the polytropic index. Okay. Okay, so for different values of n, we get such for n equals to n equals to gamma. So this is in general, n equals to gamma, go to the adiabatic. N equals to 1, go to the for n equals to 1, we go to the, what is the process for n equals to 1? PV equals to constant. Hello. Which process PV equals to constant? For n equals to 1, that means the PV equals to constant. So yeah, isothermal, right? So in general, PV to the power n equals to constant is the polytropic process. Okay. So now if you calculate the work done for the polytropic process, okay. So once you know this formula for the adiabatic case, right? So adiabatic case, you know the formula is that the PV. So is that what is that? Yeah. So PV P1 V1 minus P2 V2 by gamma minus 1. So the similar way you get the work done formula is P1 V1 minus P2 V2 by n minus 1, right? So you use the ideal gas equation. Okay. So but for the ideal gas, let's say for ideal gas. So now you use the equations of state. What is the equations of state, and put we go to the transfer into the temperatures. Okay. Because the equations of states that the A, P, V, P0. So this P and V is related to the temperatures. Okay, via equations of state. Okay. So then we can calculate the work done for the polytropic process. Okay. So now go to the things are left. Yeah. So, okay, so now we are going to the last things that so let's say the equations of state for an for not a gaseous system. We are calculating, let's say, spring system, not a spring system. So it's a string system. Okay. So the equations of state, the equation of state for a certain substance. State of an let's say ideal elastic substance. Elastic substance is given by, let's say, if it's kT times L by L0 minus L0 square by L square. So L0 is a constant. Okay. So that means that the length, when the length of the, let's say, elastic rod or any kind of things, so the length of the rod when there is a zero tension, and L is the when put a tension, and this L actually the functions of, so this tension F, so F is the tension, so this is the tension, so this is a functions of L. This is increase the L, and this depend on the how much put the tension on the rods. Okay, and that depends on the temperature, because the thermal system is the temperature is comes into the pictures. So they depend on the temperature and L. Okay, so this tension actually depends on the temperature and L, and you can put some normalizing this L to a L0, dividing by L0 to make a dimensionless this quantity. Yeah. So then we can calculate that work done. Okay. So in this case, what is the dW? So is dW generally F dx, right? So in this case, you know that. So it's F dx, right? So it's not a PdV. For the gaseous system, is PdV, and that's why we're putting a negative sign. But in this case, there is a no negative sign. Yeah, because the x increases. That means, so I draw a diagram, right? These kind of things. So let's say this is your length L naught. Okay. Now put a tension F, and due to this increase M. So that is the same direction. Okay. So that's why there is a no negative sign. Okay. So this F dx. Now we calculate the work done W. That means the integrate F dx. Some, let's say, L1 to L2. Okay. So L1 to L2 F dx. Now you know that the F, so just put into this formula. So this dx actually convert here is the dl. So yeah, or we can write x, whatever your notation, you can write, let's say, x, and it's a function of, let's say, x. Okay. And then it changes from L1 to L2. So we are just calculating this L1 to L2, and this kt x by L0 minus L0 square by x square and dx, right? So I get a formula that kt times 1 over L0 by L1 square, L2 square minus L1 square, and then minus 1 over, sorry, L0 square into yeah, so 1 over x, so 1 over L2 minus 1 over. Okay. So now put different values of L1, L2, I get that. Right? So, yeah. Suppose you compress the system, then suppose you compress the system where I'm not increasing, dx is not positive, so that means that suppose L1 is your L naught and L2 is, let's say, uh, L naught by 2, then it's like a gaseous system. So when we put the negative sign, so that means it automatically comes in, we get this. Okay, so when your upper limit is smaller than the lower limit, we get a negative sign, right? So just keep track of this. Okay, put into this formula, what we get, this kt 1 over L0, and this L0 square minus L0 by, so 1 minus aperture, sorry, aperture minus 1, right? So 1 by 4 minus 1, 1 by 4 minus 1, and then plus L naught square 1 by L2 2 minus, so we get this what is that, yeah, L naught square, so that means that kt L naught minus 3HR plus 1, so minus, sorry, 1 minute, 4 3 एक 4, okay, we get a plus 1 by 4 kt L naught, 1 by 4 kt L naught, yeah, so there is a negative sign, just a minute, 1 by 4, yeah, yeah. So for in this case, so when we do this L0 to L0 by 2, right, so that means you so your tension is always this direction, right, and you are going to your changing x in this direction, okay, so that's why when we do put some limit L1 to L2, we give a minus sign here, right? So because you are limiting limit situation, so you're limiting, so in the so when I write this expression, this is here is always L2 is greater than equals to L1, right? So this expression is valid for this case. So this expression is valid for this case, but in these examples, okay, so this is reverse, okay, so L1 is greater than L2, okay, so then we can put, so when we write this thing, when put an extra negative sign, so that means that this W is actually minus L0 to L0 by 2 f dx, so which gives this minus this and minus this and this. So why minus sign? It's just a convention, okay, so that things that if each tension is always the putting this and you are the compress the systems, okay, so in the same way we can do in the gaseous systems, okay, the same situation appears here. So for gaseous systems, when you compress this V to V minus V, so that's why these are positives, but in this case, it's opposite. Okay. Okay. So let me stop here, and we will discuss more about the thermodynamics, the law of thermodynamics. Go to the second law, and other things are discussed in the next class. Okay. Yeah. So any questions so far, or then otherwise? Okay. So I think the assignment problems you can solve, and the most of the problem we discuss here, and other things are quite trivial, so you can easily solve. Okay. Okay. Then we will see in the next sessions. Yeah.